Okay, so we will start now. My name is Amir Shabar. I'm the chair of the Toronto Center of CMOS, and we conduct these monthly webinars, uh, provided I can find suitable people to volunteer. Anyway, before we start, I'd just like to say a couple of words about our center, what activities we're doing. Um, and one of the things that let me see if I can get this. Right, okay. So, so aside from doing funding the Toronto Centre webinar series, our membership also funds webinar honorarium. So we offer a small honorarium to guest speakers after their presentation has been given. And so we thank our member for their support and hope that they will continue to renew the membership. Membership is actually currently being renewed. November, I think, notice went out to the members, so please renew your member. If you're not a member, there is a link at the bottom and a QR code. And if you'd like for me to send you that information, just send me an email. I'll forward that to you. So that's just a little blurb on our center, what we're doing. Okay, so now I'd like to introduce our speaker. Today's speaker is Dr. David Sills. He's the director of the Northern Tornado Project at Western University. Dr. Sills earned his PhD in atmospheric sciences from York University. He served as a severe weather scientist at Environment Canada for more than 20 years before becoming the director of Northern Tornado Project at Western in 2019. Currently, David is an adjunct professor at both Western and University of Manitoba, and a principal investigator with the Northern Hail Project. He also has, he's also on the leadership team for the recently launched Canadian Severe Storm Laboratory. I think he'll talk about that quite in detail today. David has authored dozens of scientific papers, has served as associate editor for several prominent Canadian and international weather journals, and works on an international committee that is developing a new tornado wind speed estimation standard. David was awarded a Ruth Bornstein Medal in 2017 for his contribution to operational meteorology in Canada, and has also been named Western University Newsmaker of the Year for 4 years. So over to you, David.
Great, thanks, Amir. And hello, everyone. I'm just going to start sharing my screen. Yes. Share. Hopefully all the technology works. And go here. And one more thing, hide the floating meeting controls. So that should do it. Okay, great. Great to see all of the familiar faces and names on the Zoom call. And so I'll be talking about this new era in data and research related to thunderstorm hazards. Lots of exciting things happening. And I've been the Northern Tornadoes Project director since 2017. And as Amir said, on the leadership of the CSSL since we launched that in October. And I'll be talking about that as well. And the tornado you see in front of you is one I'll be talking about in this talk as well. That's the Didsbury tornado from 2023, the most recent EF4 tornado. So a rare beast and a great photo from David Hart there. And I'll advance, I hope. There we go. So what I'll be talking about, the launch of the CSSL, as I said, that was in October. And then focusing a bit more on the Northern Tornadoes Project and its evolution. So how we started the project in 2017, how we initially focused it and then increased the scope, how we detect and assess tornadoes, some examples of extreme storms, and including that Didsbury tornado, some new data sets and tools that I'll talk about. Then a little bit about the Northern Hail Project, which we launched in 2022. And again, both of these projects are under the umbrella of the CSSL. And that was with the partnership of the ICLR and also funded by NSERC through an Alliance grant. And then a Northern Mesonet Project that we launched as we launched the Canadian Severe Storms Lab. So that was 2024. And then I'll also discuss a bit about the plans for the new CSSL. So I thought I'd start here with, where we are as far as thunderstorm impacts in Canada. And this is a list of the top 10 disasters by insured losses from CATIQ. And, of the top 10 insured loss events due to natural disasters in Canada, 6 of them, the ones in red, are severe thunderstorm events. So clearly, the impacts from severe convective storms in Canada are large. And actually, I've included some of the latest events from this year on this list. And, it's the Calgary hailstorm has jumped to number 2 with almost $3 billion in insured losses. So, these include thunderstorm-related damaging hail, flash flooding, derecho with tornadoes. So all of the hazards are part of this list. And there's over $8 billion in insured losses that come from severe convective storms. If you adjust those to 2024 dollars, the numbers go even higher. And of course, these are just the insured losses. It's at least as much for uninsured losses, sometimes more than double the insured losses. And as I said, there are 2 entries from 2024, 4 in the last 4 years. So this is working out to about $1 billion plus event per year that's happening in Canada. And so the pace of the losses here are really increasing for a number of reasons, but climate change has probably got something to do with it. We've got a lot more work to implicate climate change directly, but clearly the number of these massive losses is going up. So that's part of the reason for launching the CSSL. So the Canadian Severe Storms Laboratory, we launched it October 28th, 29th. This is a partnership between Western and Impact WX, which is a social impact fund out of Toronto. And so that donation is $20 million over 10 years. So this is going to sustain the CSSL and everything that comes under it for the next 10 years. So we've got some long-term funding. The vision here is that the CSSL is the authoritative source for severe convective storms research and data in Canada, and of course, improving the safety and well-being of Canadians. But, there is the the National Severe Storms Laboratory in the US, and that was established in the 60s. There's the European Severe Storms Lab in Europe, and that was established in 2006. So the idea here is that we're following in the footsteps of these other SSLs and joining the club per se, with focusing resources, focusing knowledge in the country for severe storms. And that's a photo from the symposium that we held on the 29th at Western or near Western. And you can see there was quite a crowd taking in all of the international speakers and Canadian speakers that we had to celebrate the launch of the CSSL. So Dr. Greg Kopp is its director, and he's an engineer, a wind engineer, who has been at Western for 20 plus years and has also been, he basically co-founded the Northern Tornadoes Project as well. And again, the NTP and the NHP are under the CSSL umbrella. There's also this new Northern Mesonet Project I'll explain. And in the future, we also want to tackle flash flooding, which is going to be a big one to try to get to try to get a better understanding of in Canada. So I'll just focus right now on the Northern Tornadoes Project and what we've managed to do with that. And you know, I don't want to assume that everybody has got knowledge of all of these terms. Even what is a tornado? Sometimes experts agree on what a tornado is, but this is what we say at the Northern Tornadoes Project, and it's also basically the same definition that comes out of the AMS glossary, in that a tornado is a violently rotating column of air that extends through the lower part of the thunderstorm to the surface, which can be land or water. And the vortex over land is made visible by a funnel cloud and dust and debris over land. And over water, it's likely a funnel cloud plus a spray vortex at the surface. And you know, just to give you an idea of how difficult it is sometimes to know when you're looking at a tornado, this was the EF3 tornado in 2018 near Ottawa. And yeah, you don't see much of a funnel cloud there, just a little funnel cloud protruding from the base of that cloud, but you can definitely see where the impacts are occurring at the ground. There's a power flash there where the power is going out because the tornado is causing damage at the ground. So, you know, not what you'd think is a classic looking tornado, but certainly a powerful one. And on the other hand, this is water spouts over Lake Huron. And in this case, we do have the condensation funnel, the funnel cloud extending all the way from cloud base to the surface. And with that middle one there, and also the one on the right, you can see that there's spray being ejected because of the wind speed at the surface. So this is the spray vortex. And that's basically our definition when we have pictures sent to us like this of water spouts, is that it needs to have some evidence that there is tornadic strength wind at the surface, and that is the spray vortex. So that's what it takes to be counted as a tornado in our database. And then there are downbursts. So while we're looking for tornadoes and finding damage due to wind, we often are finding downbursts, and these are damaging storm downdrafts caused by the storm's precipitation evaporating and also precipitation loading within the storm, the force that the precipitation has in the air around it. So these are two things that are causing most of the damage due to wind, the tornado and downburst, and their damage patterns are quite different. With the downburst, you've got downward directed air from the thunderstorm, and it's spreading out as it hits the ground, and you get this vortex ring along the leading edge, and basically diverging winds at the surface. While with a tornado, you've got air coming in toward the thunderstorm, you've got this vertical vortex, and so there's this convergence at the surface and air going up into the thunderstorm. So with downburst, I like to say it's down and out, and a tornado, it's in and up. And that's the most simple way to describe these two things. But clearly, if this is happening over a forest, you're going to get very different tree fall patterns from one compared to the other. And we certainly use that when we're assessing whether damage is tornadic or due to a downburst. And then rating tornado damage, when we started rating damage in the US and Canada, it was the Fujita scale that was implemented. And this is the scale, the speed scale that was implemented in Canada, going from 0 to 5, and going from 60 kilometers an hour all the way to 510 kilometers an hour. Studies in the US had showed that the low end was too low, the high end was too high as far as the wind speeds go, so the enhanced Fujita scale was developed, and it was implemented in the US in 2007. It took me a while I was in Environment Canada to figure out how to get it approved at Environment Canada, but by 2013 it had been implemented. And you can see in the new red table there, these are the new wind speeds associated with the EF scale. So going from 90 kilometers an hour to 315 or more at the upper end. And all of these damage indicators along the side with barns and family residences, motels, schools, high-rise buildings, towers, and then these last 6 at the bottom here, where we either revised the DI that the US was using because of new knowledge since they had implemented it, or things that we had introduced like farm silos and grain bins. And just to show you the power of a 5-level tornado, this is the Eli, Manitoba tornado from 2007 and rated F5. and you can see all of that debris in the air. But what's most impressive is that this is an entire house that's been taken off its foundation and thrown through the air, and was a well-built house. So this clearly meets the definition of F5 or EF5 now, and that's actually the only 5-level tornado that's been recorded in Canada so far. As far as tornado climatology goes in Canada, the first attempt at it was made by Michael Newark of the old AES, which is now, of course, the Meteorological Service of Canada. And he took data from 1950 to 1979, so 30 years, that he collected basically on his own through searches of newspapers and libraries. And actually all of that material that he collected is now available online at Western libraries. If you go to newarktornadoarchive.ca, that's where you'll find all of his original files and his analyses, some of which have been updated since then, but it's all the original work is there. So what he came up with as far as a climatology, using the data and some extrapolation is what you see here. And it's hard to see where all these lines are, but the numbers are showing where he found maxima. So it was basically the southern prairies is where the numbers were the highest. These green lines are where there are elongated minima, and along the Rockies, that makes sense. But some of these other minima are a little strange in how they came about. I'm not sure what was the reason for those being put there. But roughly, and in Southern Ontario, that was the highest. Southwestern Ontario into the GTA area is more than 2 tornadoes per 10,000 kilometers squared per year. So it had the highest rate of occurrence. Overall, it was roughly 25 tornadoes per year on average over that period. And we have that data, and when we're extending our databases back further, we'll definitely be trying to include that data that Newark came up with. It needs some quality control to be able to be plotted properly and that kind of thing, but it's certainly something we're working on. Then we came up with a new 30-year database, starting where Newark left off. So this is 1980 to 2009. And the whole reason behind doing this was to come up with an area or an idea where tornado-prone areas are in Canada, and that was for Canada's National Building Code. It needed to know where tornado-prone areas were in Canada. So we took all the data between 1980 and 2009 from offices across Canada, weather offices, and any other source we could find, and came up with this map that shows all of these dots of where tornadoes had developed. And the small pink dots are the F0s. You can see how many there are compared to the higher intensity. And there's that Eli tornado, that black one over in southern Manitoba. So we had an idea of where all the tornadoes had occurred over that 30-year period, but it also matches very closely to a population density map of Canada. And what this red line shows is where we know there are a lot of severe thunderstorms that are occurring, but we don't have many reports from there. So we knew we were missing a big chunk of tornadoes that were happening in that red area. And there was 61.3 tornadoes per year that were verified across Canada based on these observations. And we needed to know how many occurred across Canada when you included tornadoes that were in this big gap area outlined in red. So that was the challenge, and how to fill that gap. So what we did is used a statistical analysis that used as input all of that tornado data, plus population density data, and also lightning data, since we had such a great lightning database that extended back to 1998 from the Canadian Lightning Detection Network. And this gave us a prediction of the tornado frequency. And as you can see, it filled in that red area quite well. And now the model was saying we should be getting something closer to 150 tornadoes per year across Canada. So the number has, as you can see, extended or increased each time we look at this with more data. So we know we were missing tornadoes. Something else that's interesting is that when we do the modeling, those green minima over the Rockies, that turned out to be right. But you don't see those other minima that that Newark found over the prairies and over Quebec, what you do see is that northeast of cold, deep Lake Superior, there should be a minimum in tornado activity as well there. As far as where the maximum areas were, southern Saskatchewan was painted as the place with the highest tornado occurrence, and then again, not quite as high, but down in southern Ontario was also thought to be, or also shown to be from the model, a high region for occurrence. So, this is currently guiding the building code as far as, where tornado prone areas are, but is it correct? And it is a model and model results. And so there's a chance it's not correct. We did our best with the data we had, and it looks good, but we didn't know if that was actually what was happening. So we needed even better tornado observations to know for sure. And we talked to, again, this Impact WX, this donor, about an idea to try to figure out how tornadoes, or where tornadoes are occurring in that red area, basically in our forests, where these tornadoes are happening, how strong are they, these kinds of things, and got funding to start a Northern Tornadoes Flyover project in 2017. So this was a pilot project. Basically, can we detect tornadoes in Northern Ontario, Northern Quebec that would be missed otherwise? And how we were planning to do this was fly aircraft over suspected tornado paths and find and document damage paths. And it turned out to be a pretty slow year for tornadoes in Northern Ontario, but there was some activity going on in Northern Quebec. And in fact, that later that year, or actually early 2018, we found high-resolution satellite imagery was being collected on a global basis, on a nearly daily basis, by a company called Planet.com. And so we were able to subscribe to that service and really scour the satellite data for evidence of tornado damage. And what we found was a 2-day, 24 tornado outbreak in Quebec that occurred both on the 17th and 18th of June in 2017. This is the largest outbreak in Quebec history. This is the largest 2-day outbreak in Canadian history. So we knew we were onto something here because, we're finding a big outbreak that really wouldn't have been known about otherwise. So based on that success and success in the next year with an extension of that pilot project, we actually started the Northern Tornadoes Project. You can see where the name comes from now. And again, that's at Western with funding from Impact WX. And again, we're mixing people, mixing disciplines together at Western. There's no meteorology program there. It's a wind engineering program. So there's wind engineers, but we brought on meteorologists. We have GIS specialists at the library. We even have a social scientist from York University, Jen Spinney, that we have help us to do this kind of work, looking at all aspects of tornadoes and tornado climatology in Canada. So you can see along the left side there, Greg's in red here, and then our team, with Leslie, Connell, and Aaron, and Dylan, and so on, down on the staff side. And on the right side is all of our partners. So Impact WX, the University of Manitoba, John Hanasak there, York University with Jen Spinney, but also the Weather Network, Instant Weather, CatIQ, and we've also worked closely with Environment Canada, both on the science side, the S&T side, and the MSC side. But the goal of the project is to advance our knowledge of the true tornado occurrence and risk across Canada. For every tornado, we want to detect, assess, document, and make public all the information. Conduct research to improve how we detect tornadoes and maybe even predict them, and then use the data for things like building that climatology, for risk assessment, warning verification, even assessing the influence of climate change. So how do we detect and assess tornadoes at NTP? A lot of our events start with a social media post, and there's one here at the top left from the Scarth tornado back, when was that? 2021, maybe? In Manitoba. And, this was the first indication that this was happening. So sometimes it's right away, that there is a tornado. There's no doubt about it. Other times we just get something that may look like a tornado. We have to do some more investigation, or we get photos sent to us through social media of possible tornado damage that we have to investigate. So we're using social media quite a bit. We use radar quite a bit. You can see at bottom left here where we're using the multi-radar, multi-sensor system from the US that incorporates Canadian radar data to look at tracks of things like hail or rotation and give us an idea where long-lived thunderstorms, supercell thunderstorms may have gone through and created a tornadic damage. And of course, looking at radar data itself, here's a big hook echo associated with that EF3 tornado that went northwest of Ottawa through the Dunrobin area in 2018. So, we're really active on social media. We've got our, Twitter accounts and our X accounts. We've got Blue Sky accounts. We've got all kinds of different accounts. People can report to us through those accounts. We also have super contributors on social media who actually seek out reports on social media and send them to us, and sometimes even do their own little damage surveys if they're nearby. But like I said, one of our primary sources of data now is satellite data from Planet. That gives us 3-meter data, and this is what a tornado looks like going across the landscape, the damage in a long, narrow path. And if we could zoom in even more, we'd see convergent tree damage there. And in cases where it's not clear from the satellite imagery whether it's a tornado or a downburst, we can bring in aircraft data, fly aircraft over it, and you can see you get a better picture of the way the tornado caused the damage, the tree fall directions and that kind of thing that give us clues as to whether it was a tornado or a downburst. That's 5-centimeter imagery. But more and more, we're collecting drone imagery at less than 2 centimeters. And at at that resolution, you're seeing, the details of every tree, the details of the soil, all of the direction of information, of course, even damage to buildings and that kind of thing. But we also want to do ground surveys. So we have the wind engineers on the team, plus all of the interns we take on, and I'll talk about that later, doing ground surveys and characterizing all of the damage that occurs to come up with a damage rating. So, it's a process that we go through for every tornado. We create these event maps that we gather from social media. So every one of these labels here is something that's come from social media or some other report, and you can click on those and actually get the source of that. But we also have an app that we use in the field that's really transformed how we do our work in the field. This is a Survey 123 app from ArcGIS that the libraries put together for us. We can record all of the data on time, location, from GPS, the damage indicator giving us what level of damage, record the photos from that area, and that data can be sent back over the internet, and I can actually watch the team work in real time as they're somewhere across the country collecting the data. And then once all of that data are collected, we put together investigation maps. And here you can see in the dark line here where the team has gone, so their track. All the blue is where they've used the Survey 123 app and recorded a photo and other information. And then the orange is where the drone has been flown and taking photos. And again, all these things you can click on and see the source data. So that's how we gather all of the data that we use to determine if a tornado has occurred and how strong it is, how long it is, all these things. We work collaboratively with Environment Canada on preliminary assessments, and we want to get those out 24 to 48 hours after the event typically. Especially for significant events, we'll work collaboratively, sometimes even doing media together, such as with the Didsbury tornado. But it takes us a lot longer to do a final assessment. We want to make sure we've got all of the data, not just what came in the first 12 or 24, 48 hours. We want to make sure we've got all of the satellite data, which sometimes can take a little longer to come in if it's cloudy and that kind of thing. Make sure we've scoured all the social media, collect all the data to make for a complete assessment. And that can take weeks or even months, depending on the type of event. So here's where all the data end up on our NTP dashboard. So this is kind of there's the GIS backend, and this is the front end where people can access the data. So there's ways to filter the data, descriptions of the different types of data. You can see the totals along the top. So from 2017 to 2023, we have confirmed 704 tornadoes, and those this is a plot of all of the events, including the tornadoes, downbursts, everything else we collect, and that's 1,620 events. So that's what's plotted here over 2017 to 2023. And again, you can click on any of these events and drill down to the source data. So this is the Didsbury tornado. So you get a description of that event plus the link. And if you go to the link, then you get the event summary map, which gives you all the photos, all of the drone imagery along the track, the actual center line that was assessed, where the worst damage was, what the rating was. That's a 4 there, so an EF4. And you can zoom in and click on any of the data that's there to see all of the source imagery. So if we just look at just the tornadoes from 2017 to 23, it's about 100 tornadoes per year. So this is more than the 61 from just the 1980 to 2009 climatology, but it's less than 150, which was the number of tornadoes that the model told us that we should expect. So, you know, there's probably quite a few more tornadoes that we're not able to assess, and those are probably the weakest tornadoes. The EF0 defaults that we use when there's no damage, but we can see that a tornado is occurring. So there's a lot of tornadoes that occur in the forest that are maybe EF0, but the satellite data is not able to pick that up. So we know that there's still more to do. But it's interesting because if you look at those areas the model had shown that were minimum areas, that's over the Rockies, and that's certainly showing up in our data. And northeast of Lake Superior, that's certainly showing up in our data. Where it starts to differ is the model was saying that the southern Saskatchewan was going to be the real hotspot across Canada. And we haven't really seen that. It doesn't show up as a hotspot. In fact, the 2 EF4 tornadoes that have occurred have been on either side of Saskatchewan, one in Manitoba and one in Alberta. But look to the east, and there's a lot going on in Ontario and Quebec, including EF3 tornadoes over that period. So not expected. That was something that we really didn't see coming. And here is a close-up of that. These are all the tornadoes in Ontario, Quebec, and New Brunswick between 2017 and 2023. It's 57% of all the tornadoes in Canada are occurring in this region. And you can see that a lot of them are occurring in the Ottawa area and to the northeast. And you know, a lot are occurring in the forested areas as well. And that's why we'll be able to pick those up now with the satellite imagery. Interestingly, down in London where we are, and down to Windsor, this used to be known as, you know, Ontario's and certainly Ontario's and maybe even Canada's tornado hotspot down here. And we haven't seen an EF2 tornado since 2017 down in this area. So there's some interesting things happening. And, you know, it's hard to know if this is a longer term trend or just something that's occurring over this short period that we've done the project so far. These are the tornadoes in 2024. I say so far because we're still not finished with the review and adding tornadoes in. We do a satellite review at the end of every year to make sure we didn't miss anything. So all of Canada is looked at again through satellite imagery. So I believe there are some more tornadoes that are going to be part of this. But right now, the total stands at 113, 92 over land, 21 over water. But what's interesting, again, 58% of the tornadoes and all seven of the EF2 tornadoes that occurred in Canada were in Ontario and Quebec, and fairly quiet on the prairies once again. So just some NTP highlights between, you know, the start of the project and this year. We've thoroughly documented major Canadian tornado outbreaks, the 2017 tornado outbreak I mentioned in Quebec, another outbreak in Ontario and Quebec in 2018, another one in Ontario and Quebec in 2021, 2 EF4 tornadoes, one in Alonsa in 2018 and one in Didsbury in 2023. We spent a long time documenting Canada's deadliest and costliest wind event, which turned out to be the Ontario-Quebec derecho in 2022. That included 4 tornadoes to EF2 strength. Also some first, you know, the first damage survey north of 60, which was just north of 60 at Fort Smith, Northwest Territories in 2019, where there was an EF1 tornado. The first recorded fire tornado, that was Gun Lake, BC in 2023. We probably have the world's largest collection of wind damage Aerial imagery now, 5 centimeters or better, because we've been doing this systematically, and we've got lots and lots of data that the library's been archiving for us. And we've so far documented events in every province and territory in Canada except Nunavut. So far, Nunavut has eluded us. We haven't been able to find any damage there. Not a lot of trees there, but and not a lot of communities either. So surely there are tornadoes that occur there, because we do have an account of an event in Nunavut from the past. But since the project has started, we haven't documented anything in Nunavut so far. So some examples of extreme storms documented by NTP. Again, the Didsbury tornado. This was an EF4 supercell tornado that tracked 15 kilometers between Didsbury and Carstairs. Only one minor injury, and that was due to a first responder getting cut, I believe. But these things, as EF4 tornadoes, have the potential for just catastrophic damage and loss of life. With the last one in Alberta was the Edmonton tornado in '87, where there were 27 fatalities and hundreds injured. And you can see the damage caused by this tornado. Thankfully, the people that were affected, basically 1 or 2 farmsteads that were in the way, managed to get the warning and get out of the way. And the red circle is around the team there to give the damage survey team, just to give you a sense of the scale of the damage there. And this is, one of the farmsteads that was really damaged. That's the before image. That's the after image. So lots of devastation, 3 homes, including one that was rated EF4, 11 barns and outbuildings, 4 grain silos, a mobile home, a long list of vehicles and farm equipment that was thrown. In fact, there was a 10,000 kilogram combine that we've documented was tossed 85 to 95 meters and then just landed, went over a building and fell out of the sky. So we definitely are using that kind of information to try to get an idea of the wind speed. I'll talk about that a bit later. And there's the the track with all of the drone imagery we collected. So all of that green there is all the drone imagery down to 1 to 2 centimeters resolution. So we've got incredible data from this event. It even did a loop after it caused the worst damage, as you see in the middle there with the EF4, the 4 that's in the middle of the page. The other extreme event that I'll talk about is the 21st of May 2022 derecho. This had a nearly continuous damage path, 1,000 kilometers long, but 100 kilometers wide. Because it went through the Windsor-Quebec City corridor, it actually impacted Canada's most populated region, about 41% of Canada's population. There were several downbursts causing EF2 damage, so winds estimated up to 195 kilometers per hour. The maximum recorded gust at an airport was 147 kilometers per hour, and 16 fatalities. That's a really, really high impact event. At least 12 injuries, but we believe there were a lot more. It's just very difficult to get injury information in Canada. So the deadliest derecho in Canadian history and the most fatalities due to a thunderstorm event since 2000, the Pine Lake tornado. As far as financial losses, 1.2 billion plus in insured losses. It's Ontario's most costly natural disaster, one of the most costly in Canada. And, it's our best documented derecho up to this point. And this is why. I mean, this is all of the data that we collected, all of the satellite imagery that was analyzed, everything, every icon on here represents some kind of damage or observation, and there are thousands of them. And when we put all that together after months of work, this is the contour map we get. So the blue is EF0 damage, the green is EF1, and the yellow is EF2. So you can see, like I said, continuous damage from basically London to Quebec City, and sometimes getting up to EF2, especially Ottawa got really hammered by these downbursts and EF2 downbursts there that had a huge impact on the electrical infrastructure in that area. And we are working on trying to see how rare these events are. We've got a derecho climatology that we're working on. You can see events here from 1922 in the Southern Prairies to our 2022 derecho that, again, went from southwest to northeast. But you can see that a lot of them go over the Great Lakes area. The main axis in the US is just southwest of that, just southwest of the Great Lakes. It's possible that axis could move more towards the northeast with global warming. and we could be experiencing these things a lot more often. Let's hope that's not the case, but that's certainly a possibility. Just a bit about new data sets and tools. We built the data set back from 2017 to 1980. So we've got nearly 3,000 tornadoes in this database now. And we created a new dashboard to look at all this data. So this is an advanced dashboard with some more features than the main dashboard. You can look at the actual tracks of the tornadoes. There's more ways to filter them and so on. But it also includes a new 1991 to 2020 30-year climatology. So this is a new updated 30-year climatology for tornadoes. And I'll show some info from that in a second. But this is a close-up on Southern Ontario, where you can see all that track information can now be plotted back to 1980. So yeah, we've got these two 30-year databases now that are really high quality, 1980 to 2009 and 1991 to 2020. And the most active province does change between those two, from Saskatchewan in the first climatology to Ontario in the second climatology. Something that's really interesting is that the number of injuries and fatalities has really changed from the first to the second climatology. Injuries from an average of 31 per year down to 11.4, fatalities from 2.1 down to 0.8. So something's going well here. We've got the number of injuries and fatalities going down just in that shift of 10 years of the 30-year climatology. And looking at the prairies versus Ontario and Quebec, definitely see that in the first climatology, that 30-year one in blue, the number is going down. On the prairies to orange, which is the new climatology, in Ontario, Quebec, it's going up. There is a bit of change of seasonality too. In the new climatology, things are occurring just a bit later in the year. That's something we've certainly seen in Southern Ontario. But there are studies in the US that say there's this eastward shift in tornado occurrence going on. So that may be happening here, but it also may be a function of how we're doing things. We've got, with NTP, we've got many more satellite-based detections now, and many of those are Ontario and Quebec. So is that affecting the climatology? Is the fact that we're more accurately getting the numbers for Ontario and Quebec, making it look like their numbers are getting ahead of those in the prairies? And that's something we have to keep in mind for sure. And we know that that's a possibility. So we're working on ways to detect tornadoes better in the prairies with satellite data and looking at vegetative health. But it will likely require the next 30-year climatology, 2001 to 2030, to be more certain about any changes that are going on. So how have NTP data been used? We've done an overview paper, all these peer-reviewed studies looking at tornado risk and design, forest damage, satellite-based tornado detection, trend analysis of the extreme events, tornado warning verification, environmental analysis, so the events for strong tornadoes, using our downburst data to do downburst analyses out of McGill. So the data are being used in really creative ways. And one of the things that we're working on right now is trying to estimate tornado wind speeds based on things like that combine flying. So this is a debris flight analysis that Connell Miller in our group has been doing, looking at various large objects and how they're being transported. And what we're finding is that the winds required by engineering analysis to do these things are actually higher than the tornado ratings, the official tornado ratings of EF3 and EF4. And we're finding similar things with the tree fall pattern matching. And what's going on here is we look at tree fall patterns using the drone imagery. We match that to tornado modeling that includes wind speeds. And then we can find estimated wind speeds based on the patterns of tree fall. And what the tree fall pattern ratings are showing us is that something that we can only rate EF2 based on the EF scale as far as forest damage could be EF3, maybe EF4. So that work has been submitted, and certainly if we find that we can do this in a reliable way, we will be able to re-rate a lot of tornadoes in the forest to higher tornadoes based on this method. I'm just going to skip this in the interest of time. Yes, the project is successful and nimble, and it's made possible other projects such as the Northern Hail Project. So we expanded scope in 2022. This is the Northern Hail Project starting up. Julian Brimlow is the director. We're focused initially on Alberta's hail alley. That's the biggest problem in Canada for hail. But we're also conducting hail damage surveys nationally now and working towards a national 30-year damaging hail climatology. And that work can be found at that website there. So this is work that, again, is in partnership with ICLR and funded by NSERC and MyTax. We've got a lot of work to do, all these tasks that we've listed that will result in advancing our knowledge of hail with benefits to Canadians. We've done a lot of work in the field as far as basically chasing tornadoes with these teams, chasing hailstorms with these teams so we can get behind the storms and collect the hailstones before they melt. Look at the numbers of kilometers driven. We're talking about, thousands and thousands of kilometers driven to get these hailstones and complete these damage surveys. So we can also use drones to sample these hail swaths, and as well as recording the data, and use radar as well. So this is the 2022 and 2023 hail swath analysis using the hail algorithm that's in radar, the mesh algorithm. And you can see how many hail swaths occur across Canada. Obviously, not all of these are going to be extremely damaging, but there's a lot of hail falling, mostly in Western Canada, but you can see in Eastern Canada also that we do have quite a bit of hail. And then doing hail damage surveys. So this is basically forensic level surveys of hail damage that's occurred in communities. And we're doing more and more of these to try to get a sense of how hail is causing damage to buildings, to infrastructure, to crops, and these kinds of things. And you can see this is where hail damage surveys were conducted in 2022 and 2023. And this year, with the $3 billion Calgary hailstorm, we conducted the largest hail damage survey ever conducted in Canada. Spent almost a week out in the Calgary area with multiple teams documenting all of the hail damage that occurred with that storm. I mentioned that we've also started a Northern Mesonet Project. This is led by Connell Miller, who was with the Tornadoes Project, but is now leading this project. And the idea here is evaluating the utility of regional surface station networks built for extreme and severe and extreme storms. So we know that the way that current weather stations are built, they don't do well at detecting extreme storms, like extreme hail, extreme winds, extreme rainfall. So we want to explore ways of collecting that kind of data. But we're also trying to be a central repository and access point for all publicly available surface weather data across Canada. So basically a network of networks approach in real time, but also archiving that through this Canadian Mesonet portal. So yeah, with the enhanced networks, we want to do a hail network out west, a wind network in Southern Ontario, a rain network in Montreal. We started on that hail network. We've got hail distrometers to record hail occurrences centered around Calgary and in the foothills north of Calgary. There's 20 stations there, 9 to the north. And here's all of the stations that we're bringing in real time across Canada. This is all publicly available surface station data that, I think for the first time is being brought together in one place. And so we're working on ways to best use this data in real time and through archiving in order to have more information available for severe storm prediction and case studies, and even automated detection of severe winds and that kind of thing. And that's an example of, if you zoom in on all of these dots, this is what you get. You get the standard WMO type display, but also you get the history at that station, and you can do that for any of the stations that we have in our network. So just to get to the plans for the CSSL, as I said, Greg Kopp is the director. He's also the Impact WX chair in severe storms engineering and a senior wind engineering professor. Right now, we're establishing partnerships for the advisory council and looking at collaborations. So at the moment, we've got Windy, which is the the tornado and downburst simulator at Western. That's a partner, and also Palmarex and Environment Canada. We've got an agreement, a collaborative agreement with S&T to work on those kinds of things, and ICLR as well is a partner and on the advisory council. So what we want to create again is have a hub or a portal for severe storms data and research. We're going to be adding that flash flood project that still needs to be established. We also want to work on a social science storm impacts component that's more than just what we have currently. There's a new engineering building being built at Western, and we're going to get the top floor of that building for offices. There will be offices for assignments from other places if you're interested. Sustainable funding, like I said, with this donation over 10 years, hopefully many more. And we do hire a lot of undergraduate interns to help with this project. And I'll go to this graphic here, which is, shows us what's possible. So we bring in about 20 undergraduate interns every year. Some are even senior high school students. And the application deadline is January 27th. So if you've got undergraduate students, or you are an undergraduate student and you want to be involved, you don't have to be a meteorologist or an engineer. You can be from any discipline. As long as you have a passion for severe weather, we're interested in having you apply. So please do. And that's it. It's almost the holidays. So I'll say happy holidays from the Canadian Severe Storms Lab and end it there.
Okay, thank you, David. So we open up for a question. So before you ask your question, please unmute your microphone.
Well, if no one else is going to jump in, it's Peter Taylor. There hasn't been any mention of numerical modeling. And I just wonder if, given this vast data set that you're collecting, could you look at trying to do hindcasts or looking at forecasts of the mesoscale weather features that are linked to these tornado events? Could one run high resolution jam or WRF simulations of some of these cases?
Sure. Well, number one, as I said, Western doesn't have a meteorology department, at least not yet. And so, we don't have the capacity with numerical weather prediction. What our focus on is collecting data sets and hoping that NWP focused people will use these. And John Hennesack is doing some work on that. He's been looking at some modeling aspects and what parameters are required for strong tornadoes and that kind of thing. We've also hired at Western through the physics and astronomy department a new severe weather scientist who is able to run storm scale modeling. And so she just got hired in September, and we're hoping that we can work with her quite a bit more on simulating storms in an idealized setting and working with that. But like I said, the main focus for CSSL is going to be on building these data sets and building these climatologies. So not on the NWP side.
No, but it's something that other people could maybe take advantage of.
Oh, well, we certainly hope that's the case. Yeah, that's we want to make all of our data as available as possible. We do have kind of restrictions on commercial use of the data, but otherwise for academic use, for student use, for municipalities, it's all open access. All the data that we collect, all of the survey, or all of the climatologies that we do, everything's available. And if people want to use it for numerical weather prediction, please do.
Okay, thanks.
Any other questions?
Yes, it's Stephen Cleveland. Can I ask a question, please?
Hi, Stephen.
Hi. I wanted to ask, as a resident of Toronto, I'm interested in what's happening locally in Toronto, and it's my impression that there is a minimum of tornado risk occurrence over most of the GTA, Greater Toronto area. And looking at scanning those scatter maps that you're showing of occurrences of thunderstorms, it looks at tornadoes and stuff. It looks like there's a general minimum of occurrence over most of the Greater Toronto area and eastward, but a tendency to an increase towards northwestern edge of the Greater Toronto area. What do you think about this?
Sure. Well, I gave the example of Lake Superior, and very clearly you can see that there's no tornadoes occurring to the northeast of there. And you know, it's the same thing happening to the lee of all of the other lakes. It's not quite as significant as downwind of very cold, very deep Lake Superior. So in the Toronto area, you've got lake breezes, as we've discussed for many years. We've got lake breezes that develop over Lake Ontario and move inland, and so there's a bit of protection for areas like Toronto that you know, the lake breeze moves inland enough that a lot of the area in Toronto and downwind of Lake Ontario gets into this marine air mass, and thunderstorms don't survive, and therefore you don't get the tornadoes there. But as we've seen with something like the Goderich tornado in 2011, there's nothing is completely protected. We had that tornado, an F3 tornado, start and develop right over the lake and come inland, basically due to mesoscale boundaries being over the lake. So, you know, you can't count anything out because you're in one of these lake shadows, but it certainly does reduce the frequency, and you see that in Toronto.
I would hypothesize, you guys can look at it in more detail if you wish, that if the cause of the reduction near Lake Ontario or Lake Superior, maybe it occurs near Lake Huron and Georgian Bay, that there's a reduction in the occurrence of tornadoes because of the cold water of the lake, that effect should be strongest early in the season, like May, weaker later on, such as August, because the water is steadily warming and the cold water effect is becoming less. What do you think about this?
Yeah, I mean, my PhD was on this kind of topic, right? So, and what's in the literature on this is that it doesn't matter so much the temperature of the lake, as long as there's a big enough temperature difference between the air over the lake and air over the land, you can get the lake breeze, even in late August into the fall months. So the temperature of the water doesn't matter quite as much. It results in a bit more intense of a circulation, but you'll still get lake breezes that can shut off convection even into late August in Toronto. I think the hazard in Toronto, that's the bigger hazard, is the flash flooding, and we've certainly seen that. We had that nearly $1 billion flash flood event in the GTA this year, and we actually did our first flash flood damage survey out of Western this year, just to try it out and see what we can find. So it was really interesting because, you know, what do you look for in a flash flood? And so there were, you know, we definitely saw that there were some surveys are important even for flash floods. You find things that you can't find in other ways through satellite imagery, through other various imagery. But yeah, I'd say that in Toronto, the bigger threat is from flash flooding and not from tornadoes.
Okay. Well, it's nearly 1 p.m., but I have one final question. And when I was working with Environment Canada, we did some study on tornado with Dave Atkins and others. And we found that there seems to be some weak signal associated with the El Nino La Nina cycle in Canada. Did you find anything when you separate the warm compared to the cold ENSO events?
That's a good question. You know, teleconnections and larger scale features like that certainly should have an influence. And you know, we've been so busy building the data sets that we haven't got to that part yet. where we're looking at these larger scale connections and climate change in particular, what the influence of that is. Even in the US, where they've got a much larger database of tornadoes, they found some trends are occurring, but they haven't connected it to climate change. And I don't see that they've connected it very well, at least, to some of these larger scale circulations like ENSO. So there's still lots of work to do. When you get down to the scale of tornadoes and thunderstorms that produce tornadoes, the trends that you might expect out of climate change and that kind of thing are really hard to pull out. In fact, one of the things that we've noticed over since we started the project is that these years with big forest fires across the country are years with lower tornado counts, and we were trying to figure out what it is. And we believe it's the smoke that's drifting across the country, cutting down on the amount of sunshine, radiation hitting the ground. The number of thunderstorms decreases, and the number of tornadoes decreases. So if climate change is causing more intense fires, more droughts that would lead to fires, this may end up causing less tornadoes across the country. So it's a real tangle that we have to work on of various influences on things like tornadoes as small scale features. And we'll certainly be working for a long time to figure out all of these different connections.
Okay. Well, if there are no other questions, then I'd like to thank David for a very illuminating and bringing us up to date on tornadoes and other severe events. Just a note that this presentation is recorded on CMOS YouTube. And I noticed that David has given some website and link to his dashboard. So you can find that in the YouTube when it's posted, which I think will be in a day or two. So thank you very much, David, and thank you all for joining, and have a very happy New Year. Thank you.
Great, thanks. Take care.